Let's talk about vectors. Vectors are super useful in physics, engineering, video game design, because they give you a way of talking about displacement. So if you've got something that moves around in whatever path you want, and then ends somewhere, the displacement is just the difference between where they ended and where they started. So that pink arrow represents the displacement. So one way you can talk about it is how far over and how far up did they have to go between where they started and where they ended. So if this whole thing is on a grid, you can use coordinates to describe that. So here it looks like even though the path was kind of crazy, the overall displacement was 1, 2, 3, 4, 5 units over and 1, 2, 3 units up. So as a vector, you could write that this way, 5, 3 with triangle brackets. And the first coordinate is the x displacement, and the second coordinate is the y displacement. It's normal to want to so this is how you would write a vector down. This thing that I wrote here, that's a vector. This arrow, that's a way to visualize a vector. And algebraically, it's very normal to give vectors names. So I could call this vector v. But in order to know that this v is supposed to represent a vector rather than a single number, it's customary to put a little arrow with kind of one arrowhead. Sometimes you'll see it with two arrowheads like that. But it's more normal to see v with like a little arrow like that on top. And it doesn't have to be v. You could call it a, b, whatever. You can use variable names. The point is that this thing on top is what identifies it as a vector rather than a number. So I've said that vectors represent displacement. Another way of thinking about displacement is it's a translation that takes you from the starting place to the ending place. So if you think about this as a translation over by 5 and up by 3, that's the exact translation you'd need to take this starting point and put it at the ending point. Something to notice about this is you don't actually know where this is on the grid. I didn't tell you where the origin was. So a really major idea about vectors is vectors just tell you about the motion. They don't have a place where they live on the plane. So the origin could be, way down here, or for all we know, the origin is way up here, and this is all happening in quadrant 3. So in other words, you can have the same vector happening at lots of different places. So the reason all three of these represent the same vector is because they represent the same motion. They represent the same transformation over 5 and up 3. So you can have that motion starting at any place, and that's the idea. So in the last video, we talked about a vector being a displacement, and we said that you can think about the displacement as a translation that takes you from a starting place to an ending place. And you can write the translation down in terms of its x component and its y component. So how far over and how far up do you have to go? That's called the rectangular form of the vector. But there's another way to talk about displacement. And that way is in terms of an angle that you turn towards and how far you move along that angle. So an angle and a distance. Let's get a new picture here. So for example, let's say that I start here at 7, 2. But I move in a direction that's 20 degrees up from the horizontal, and I move a distance of 17 units. I'm going to end up somewhere. And so that motion from where I started to where I ended, that's still a vector. So that arrow that I drew, that's a vector. And you could maybe figure out how to write it down in rectangular form. You could use some math to figure out kind of how far over and how far up did I go. But my point is, you don't have to write the motion down in terms of the x and y components. Instead, there's another way of writing it down. You can say that we turned through an angle of, You can say we turned through an angle of 20 degrees and went a distance of 17 units. And this is a notation that we're going to use in our class. This is not a standard notation, but what this is this is the distance that you travel, and this is the angle that you're traveling along. And so just like you can have an x part and a y part, I could choose to name this vector v. I could say vector v equals distance 17 along an angle of 20 degrees. So this way of thinking is called a polar representation of a vector. These two different ways of thinking, a rectangular way of thinking where you've got x's and y's and you're moving horizontally and vertically, and a polar way of thinking where you've got an angle and a distance. Those two different ways of thinking are going to continue to develop throughout this unit and the next unit. As a quick point of clarification, let's pretend I start here and I walk along vector v1, which is an angle of 10 and a distance of 4. And then I turn another 10 degrees and I walk along for a distance of 4 along vector v2. So vector v1, we were writing it this way. So a distance of 4 at an angle of 10 degrees. What's vector v2? Is it the same? Is it also I'm walking a distance of 4 at an angle of 10 degrees? And the answer is no. And you hopefully that's clear because you can see that these arrows look very different from each other. This one is pointed in a different direction from that one. So what's actually happening here is that even though I only turned 10 degrees from the direction I used to be going in, the angle you should think about as a heading, which is like the absolute angle starting from the horizontal. So here I was heading at a heading, or I was moving along a heading that was 10 degrees, and then I added 10 more degrees. So vector 2 is a distance of 4 units along a heading that's 20 degrees above the horizontal. So I just wanted to kind of make that difference clear.